Good evening, everyone. Today, we will be presenting our research titled Correlating Car Interior Parts Using Multi-Output Machine Learning on Benzene, Xylene, and Toluene. This work was conducted under the Computer Science program at Binus University and focuses on applying machine learning to a real-world environmental health problem inside vehicle cabins. Specifically, we explore whether patterns in volatile organic compounds, or VOCs, can be used not only to detect pollution levels, but also to infer which specific interior component is most likely responsible for emissions. The background and research problem. Most people are familiar with the so-called new car smell. While often perceived as pleasant, scientifically it is associated with the emission of volatile organic compounds released from interior materials. Among these VOCs, three compounds are especially significant: benzene, toluene, and xylene, commonly grouped as BTX. Long-term exposure has been linked to cancer, respiratory irritation, neurological effects, and cardiovascular risks. In modern vehicles, air quality monitoring systems generally only provide aggregate pollution levels. They cannot identify whether elevated BTX levels come from seats, carpets, roof lining, or background air infiltration. This leads to our core research problem. Given only measured concentrations of benzene, toluene, and xylene inside the vehicle cabin, can we predict which interior component is most likely responsible for those emissions? To address this, we formulated a multi-output prediction task estimating the likelihood of four possible sources: cabin roof upholstery, cabin carpets, cabin seats, and a clean air baseline condition. BTX emissions parameters by source. To build our dataset, we first established characteristic BTX emission profiles for each interior component. As shown in Table 1, each interior material exhibits a distinct BTX fingerprint at 65 degrees Celsius, a temperature chosen to represent unusual vehicle operating conditions. Cabin carpets show the highest benzene concentrations, cabin roof upholstery has the highest toluene levels, and cabin seats show the highest xylene concentrations. We also included a clean air baseline. These parameters served as the foundation for our synthetic data generation process. Dataset construction and pre-processing. A primary challenge is data availability. There is no publicly available dataset directly measuring BTX emissions linked to specific car interior components. We use an external urban air quality dataset containing BTX measurements and adapted it to simulate in-cabin conditions. Pre-processing steps included filtering to retain only benzene, toluene, and xylene columns, handling missing values and removing outliers from bottom and top 1%, and generating synthetic labels using Gaussian probability distributions around the source centers from Table 1. Figure 2 here shows the concentration distributions before synthetic data was added. The red dashed lines mark the source centers from Table 1. Notice the scarcity of samples on the higher end, which is why we supplemented with approximately 1,700 synthetic samples to balance the dataset. Feature engineering and models. To enhance model expressiveness, we added interaction terms: benzene x toluene, benzene x xylene, and toluene x xylene, and quadratic features: benzene squared, toluene squared, and xylene squared. Expanding from 3 to 9 features, we evaluated 4 machine learning approaches: linear regression, our baseline model assuming linear relationships; random forest uses approximately 500 decision trees, aggregating outputs to capture nonlinear relationships. Each leaf node stores 4 values representing the emission sources. Gradient boosting, which builds trees sequentially where each new model corrects previous errors. And stacking ensemble combines random forest and gradient boosting as base learners with a rich regression meta-learner and 5-fold cross-validation. All models were trained in a multi-output framework, simultaneously predicting probabilities for all 4 emission sources. Model performance results. For evaluation, we use 3 standard regression metrics: R-squared for explained variance, mean absolute error for average deviation, and root mean squared error to penalize large errors. Table 2 shows a clear hierarchy. Random forest achieved the best performance with an R-squared of 0.9593, MAE of 0.0057, and RMSE of 0.0269. Gradient boosting and stacking ensemble followed closely with R-squared scores above 0.955, confirming ensemble methods consistently outperform simpler models. Linear regression performed significantly worse at only 0.8254 R-squared, confirming the relationship between BTX concentrations and emission sources is highly nonlinear. Feature importance analysis. Beyond prediction accuracy, we analyze feature importance to understand which chemical signals contribute most to decisions. As Figure 3 illustrates, toluene is the most influential feature at approximately 0.3533 contribution. Toluene squared ranks second at 0.3408, indicating strong nonlinear sensitivity to concentration changes. The interaction between benzene and xylene also plays a major role at 0.1363, showing source identification depends not just on individual compounds, but on how they interact. In contrast, xylene and xylene squared are less important, correlating with overlapping distributions across sources. This confirms BTX-based source attribution is fundamentally multivariate and nonlinear. Random forest prediction performance. Let's examine our best performing model in detail. Figure 4 compares predicted probabilities against actual values. Each colored point represents a prediction for one of the 4 sources, and the red dashed lines indicates perfect alignment. Predictions align particularly well for clean air and cabin seats, with most points concentrated along the red line. This reflects heavier training data concentration around clean air values. Cabin roof and cabin carpets show slightly more scatter, indicating less accurate predictions due to relative data scarcity for these parameters. Random forest prediction performance. Figure 5 displays the error distribution. Most errors concentrate near zero, confirming accurate predictions overall. Clean air and cabin seats show lower error densities, while cabin roofs and cabin carpets exhibit wider histograms. Importantly, the histogram does not extend beyond the margin of 0.2, indicating the rate of misidentification remains quite low. R-squared scores per source and limitations. Figure 6 breaks down R-squared scores for each individual source. Clean air scored highest, cabin roof scored lowest, but all R-squared scores are above 0.91, meaning the model explains at least 91% of variability in every category. Onto the limitations. Despite strong performance, this study has a critical limitation. The absence of real-world in-vehicle BTX datasets means our model relies on synthetic labeling and adapted external data. While this allows feasibility exploration, it may not fully capture real emission behavior inside actual car cabins, where temperature, ventilation, and material aging affect VOC release patterns. Future work must prioritize real sensor-based data collection inside vehicles to improve validity and generalization. Conclusion and closing. In conclusion, this study demonstrates that machine learning can be used not only to detect BTX pollution levels, but also to infer likely emission sources within a vehicle cabin. Among all tested models, random forest achieved the best balance of accuracy and stability, with an R-squared of 0.9593, confirming an ensemble-based nonlinear methods are particularly well-suited for this environmental prediction task. Future research can extend this framework by incorporating additional VOC compounds, deploying the model in real-time vehicle air monitoring systems, improving dataset realism through real-world cabin measurements, and exploring detection of other faulty car components via BTX chemicals. Thank you to our audience and professors for your attention.